carboxylic acid is meta-chloroperoxybenzoic acid. That's step one. And then step two, you add the water and an acid. So sometimes you see H2O, H plus, and then you see H3O plus. Too much see. Anyway, you get the diol. And these guys point in opposite directions.
No, it really wasn't.
That's
I know.
Sorry.
Got it wrong.
You got it right.
That sucks.
Knew it.
I usually don't have to. There's always a few busters in each class, so I don't have to do that. It's hard, yeah. It's just a lot of material to keep straight. There's no doubt about that. That summary section in the end of chapter 9 kind of summarizes, all those reactions. There's a lot to remember. You got to remember which directions in space they point. That's reaction number 8. See reaction number 8 here. That's the one that forms the diol, carbon-carbon double bond, carbon-oxygen matrix, and then they point in opposite directions. All right, definitely a lot to keep straight. Okay, we finished 10 last week, and now we're going to do 11, and there's no new information in 12. So what new information read in chapter 11, and we're going to pick and choose what we want to do. Chapter 11 deals with radicals. What you've seen in most of the time, most chemical reactions don't involve radical formation, but some do. This is on page 191. So what you've seen before is what they call a double-headed arrow. This arrow has two squiggly things, whereas these guys just have one. They call this a double-headed arrow when you see that, and this is called a single-headed arrow. Anyway, all the mechanisms we've discussed so far have been what they call ionic reactions. You have pairs of electrons moving. So this bond can break, the electrons go on Y, and then Y acquires a minus charge, X acquires a plus charge. In this chapter, you're going to have fishhook, they call them fishhook arrows also. One electron be moving for single electrons, not pairs of electrons, but single electrons. So this bond represents 2 electrons, one can go on here, one can go on here. One way to do this is to keep this. Since each guy gets one electron and you have no charges, they call this homolytic because they all look the same. And this is called a heterolytic bond because one looks like has a positive line and the other has a negative line. All right, so double barbed arrow, that shows motion of 2 electrons. Single barbed arrow, called a fishhook, that shows the motion of 1 electron. So in this chapter, you will be studying reaction mechanisms that involve single electrons moving around. Okay, and there's a bunch of dance moves here. A lot of them you won't see ever, but just to refresh your memory before I get into that. A carbocation, the hybridization is sp2. You have a positive charge here. You have a p orbit that's empty. It's flat. So anytime you have a carbocation form, you have a flat sheet, and then the attacking species can come from either side, so you get a mixture of products if it's a carbocation. And then you can have what's called a carbanion, which we'll study next semester. This carbon has 3 single bonds and a lone pair. So this hybridization is sp3. So we'll talk about that. This is not flat, this is three-dimensional, this is flat. So we'll talk about this next semester. We've already covered this. Now suppose you have a radical, suppose you have a carbon with 1, 2, 3 bonding pairs and 1 electron, not 2 electrons, not none. What it looks like a carbocation, it's flat. The only difference is this is empty, p orbital, and with a radical, it's going to be 1 electron to be present. Okay, so on page 492, anytime you go through a radical mechanism, carbon is sp2 hybridized. You have a pure p orbital, and inside that p orbital you have 1 electron. Now, look for patterns in organic chemistry so you can help remember things. Carbocations are electron deficient because the carbon is only surrounded by 6 electrons. Okay? And R groups can push electrons here and stabilize. So the more R groups you have, the more stable the carbocation is. As you get 30 carbocation, the more stable. Same thing can be said about radicals. A radical will have an electron deficiency because this carbon is surrounded by 2, 4, 6, 7 electrons. So it still doesn't have enough electron density. So R groups will stabilize radicals just like R groups will stabilize carbocations. So if I ask you which is the most stable or least stable radical, it's the same concept as with carbocations. If you have a plus charge here, it's carbocations, it's electron deficient. If you have a dot here, it's 1 electron, this is still electron deficient. So for the same reason, carbocation stability follows a trend, radicals follow the same trend. The more R groups you have, R groups tend to push electron density toward this center here, the more stable it is. So if I give you a series of radicals and ask you which is the most stable and least stable, and I will, pick the one that has the most R groups, the tertiary radical, that would be the most stable. Okay, so you know that's going to be on the test. Now if I ask you which is the least stable, then the methyl radical would be the least stable. Okay, so try to remember that. What else? There's something else I was going to tell you. Oh, I know. You got to be able to draw resonance pictures. Okay, and we've done it with positive ions for the most part. Now you got to do it with radicals. So you might remember the very first or second test, you were asked to draw resonance forms involving positive or negative charges. I think we did positive charges. I can't be sure though. But if you had something like this, this is a very, very stable carbocation because you can flip this pair of electrons over here and move that positive charge around. It doesn't just have to sit on one carbon, see? So these are called allylic. This is an allylic carbocation, very, very stable, very easy to form, okay, because it's stabilized by resonance. So can you draw the resonance form for this? Now, unlike mechanisms is anything goes. You can push any electrons around you want. Lone pairs, bonding pairs, pi bonds, single bonds. With mechanisms, everything is a free-for-all. But with resonance, the only thing that you can move is pi bonds and lone pairs or a radical. That's all you can move. You can't break sigma bonds or form. You can't push around sigma bonds. Okay? You can't push around sigma or form sigma bonds. Okay? And remember, every time you see a line, that's a pair of electrons. So the resonance form, you can take this, move it in here, take this guy, move it in here, leave this guy on this carbon. So this would be a resonance form. So allylic radicals are also very, very easy to form because they're stabilized by resonance. You can spread out the electron deficiency, and that makes it more stable and easy to form. Okay, so they'll ask you to draw resonance forms. I don't know if you can do 2 resonance forms, particularly fancy here. Can you draw 2 pictures? And remember, with resonance, again, you can move pi electrons, you can move lone pairs, and you can move a radical. But you can't move this bond here. So you can't move this bond here. So if I give you that picture, I'll say, what are the other 2 pictures that you can draw? And you could do this for me, this picture. And then you can do another one. radical in this curve here. Let's see if it is. So I'll give you one picture then.
Yeah, it's like, it's not working.
Can't see what I'm treated by this. This is for special emphasis. See what it is. Let's see. Okay, so I'll give you one picture and ask you for the other picture, okay? And we're not gonna get carried away, okay? You can get carried away pretty quickly with this. I'm probably not gonna do it in a ring, because it just gets too messy in a ring. And, so I don't wanna do it on page 493, that is, page 493 in the book. Simple one. So they took this electron, put it here, this one here, on here, and this radical. And then you can really carry away if you want to, so you can move this into the ring, move it around the ring. I think we'll bypass that. Okay. Something like this, or the one we just did, be able to draw a resonance form. So I'll give you one picture, you draw the other two. Other pictures, and I'll tell you how many there'll be. There'll be one or two. All right, so that's going to come into play when we talk about radical reactions. Here are some of the. Here's another thing you want to just keep in mind. Radicals can rearrange to form more stable radicals. So carbocation, this is the second main carbocation. This is a methyl group here, a 1,2 methyl shift. This can slide over here. If that slides over there, you would get a third degree carbocation. So let's draw what it would look like. This is right to CH3 in here. Okay? So this can move over with a pair of electrons. It's a 1,2 methyl shift. You may have forgotten by now, I won't blame you. So you can go from a second degree carbocation to a third degree carbocation. So carbocations can rearrange, radicals don't. So you can't slide this over here with a radical over here. Once a radical is formed, you don't get a 1,2 hydride shift or a 1,2 methyl shift. Now, this is not resonance. These two pictures is not considered resonance. Because see, I'm moving a sigma bond. So this actually is another chemical reaction, so to speak, but this actually slides over. So with resonance, you're not really having a chemical reaction. You're just drawing several pictures to describe the structure. But if a carbocation rearranges, that's part of a chemical reaction. Chemical reactions, the arrows that show chemical reactions, you can move any kind of electrons you want to move. Single bonds, double bonds, lone pairs, radicals. With resonance, no, you're only allowed to move pi electrons, for instance. Okay. All right, so here are some of the more common, there's been too many actually, common moves you will see. And let me just show you the ones you need to know, be aware of. This one, two halogens, shine light on halogens, and they form radicals. So remember that one. Okay. Remember this one. This type of situation. In other words, if I give you this and I give you this, without the arrows, tell me how we went from here to here. If I give you this picture, without the arrows, tell me how we went from here to here. So this one, and this is just a reverse of this one. We have two of these guys coming together, so, don't worry about that one. Let's see. This one right here. So know this one, and this one. Those are the ones you're going to see in mechanisms in this chapter. The other ones, don't worry about. Okay. So when you're describing free radical mechanisms, in this chapter, this, and this, would be the ones you would use, so make sure you know those. And luckily, there's only a handful of reactions to learn in this chapter, so it's not too bad. And let me see, maybe we can get to these reactions. Let's see what else I'm scared. Yeah, what the heck, let's do this. Here's a reaction. Take a halogen. Anytime you see H nu, that means light, or you can use heat. So if you take a halogen and you bombard it with high energy light, or heat the heck out of it, the halogen will react with a hydrocarbon. This is the only important reaction of hydrocarbons. This is it. Hydrocarbons are pretty duddy. Carbon-hydrogen bonds don't react very much. The only useful reaction that involves carbon-hydrogen bonds will be a free radical halogenation. Okay? Otherwise, all the other chemical reactions involving organic chemistry will have double bonds reacting, triple bond, or carbon bonding to oxygen, or nitrogen, or sulfur, or a halogen. This is organic chemistry right here. Carbon-hydrogen bonds don't really undergo very many reactions. Okay? So this is very important because it's really the only useful reactions that the hydrocarbons undergo. And see what we did? We substituted for a hydrogen a halogen. Okay. Now this occurs in 3 steps, or 5 if you count the initiation step and the terminating steps. So you've got to memorize all 5 steps. Anytime you have free radical reactions, they tend to be a chain reaction. You initiate it and it just feeds itself, it just goes haywire. Combustion is, they think, a radical reaction. And so you put a match to a paper, and then you remove the match, and the paper is ignited, it just continues to burn. So once you initiate chain reactions that are free radical in nature, they tend to feed themselves. So you just got to give them a kick in the pants, and they take off. So how does this mechanism work? This is what I want you to learn. And again, these are the 3 important moves that you want to be aware of. First one is the what you call homolytic cleavage, where you shine light on a halogen and it breaks into 2 pieces, or heat it. So heat or light, and you get chlorine radical. Now you're going to need one of these. If you just have one of these, then the reaction just takes off. See? So you just need to take that material, give it a burst of heat or light. You don't need to continue heating it. You don't need to continue shining a light on it. Just give it a burst of light or a burst of heat, and then you're gone. Just one of these, in theory, can react millions and millions of times. Okay? So this is called the initiation step. It's not really part of the overall reaction. Okay? Now the overall reaction is this. So there's 3 steps, 3 elementary steps. When you add those 3 elementary steps, you will get the overall reaction. Okay? So the initiation step is not considered one of the 3 elementary steps. But it's important because you need to get started. It's like having a match. I need to put a match to this to initiate a reaction. Once the reaction takes place, I remove the match. I no longer need the match. So I need a chlorine atom to get this going. Once I get one chlorine atom, then it just goes. All right, so here's the very first step. Chlorine radical attacks this hydrogen, and this bond breaks, and one electron goes to this carbon, one electron goes over here to form a bond. So that's the first step, the first of 3 steps. This is a chain propagating step because it repeats itself. So you can put a dot here, and all right. So this electron goes here, this electron goes here. You form a bond, and then you have this electron stays. You put it on the carbon. All right, that's the first step. Okay. Now, second step. This reacts with chlorine. By the way, what we toss into the pot is in large quantities methane and chlorine. You have a huge amount of this. What you have a tiny, tiny, tiny amount of is this. Okay, but you don't need that. You need a lot of this amount. So second step, this methyl radical attacks the chlorine, and the same kind of reaction, kind of splitting takes place here. So this electron goes here, this goes here, you form a bond, and then you have a radical in this chlorine. Okay? That's the second chain propagating step. And then the third chain propagating step. See this radical here? It's, where is it? It's hiding. It's formed in the second step. It's used up in the first step. And it's formed in the second step. Then it's going to react. Actually, that's it, isn't it? There's only two chain propagating steps. Let me see if I can add those two together. Yes, you can. Okay. You see, I made it more difficult than necessary. There's only two chain propagating steps. See, because now this can repeat itself. This can go back and do some more of this. There's plenty of this. There's plenty of this. There's very few radicals. At any one time, this concentration is extremely small. This concentration is extremely small. It's never that big, okay? All right, so add these two half reactions together. Add these two elementary reactions together. Cancel out anything that appears on both sides. We have chlorine atom here, chlorine atom here, that cancels out. I have a methyl radical here, methyl radical here, that cancels out. So what I'm left with is methane and chlorine gas gives me chloromethane and HCl. So the overall reaction, you mix a lot of methane, a lot of chlorine. The overall reaction is that it occurs in two chain propagating steps. Okay? It just repeats itself over and over and over again. Now, you've heard of the destruction of the ozone layer. That is a process that's initiated by a chlorine atom. Radical in the upper atmosphere. The sunlight breaks chlorine into atoms from your freon. Freons contain chlorine, and freons contain carbon. Freons contain carbon, fluorines, and chlorines. Okay? They don't contain any hydrogens. In the upper atmosphere, this freon goes to the upper atmosphere, this bond breaks, you get a chlorine atom, and that destroys ozone. And one chlorine atom can destroy thousands upon thousands of ozone molecules. Because it just repeats itself. See, a chlorine atom reacts in the first step, and it's regenerated in the second step. So the process this is called step one, step two. Step one, step two repeat themselves over and over and over again. So, will this reaction go on forever? And the answer is no. You shine a light, you get chlorine atoms, the reaction takes off, and then after a while it stops. And you got to give it another burst of light. Then it goes on and on for a while, and it stops, and you give it another burst of light. So why is it stopping? Well, you need radicals. You need chlorine radicals and methyl radicals to continue the process. If those radicals are destroyed, then the process stops. Well, they're not destroyed here because I'm switching from one radical to another. Here I'm moving from one radical to another. But it's every once in a while, there's not many of these, but every once in a while, two of these guys collide and you destroy the chlorines. Or every once in a while, a chlorine atom and a methyl radical will collide and you destroy it. And every once in a while, two of these collide and you destroy that. See, so because these concentrations are always low, you don't have very much of these, it doesn't happen right away, but given enough time, two radicals will collide and basically annihilate each other. And so the process stops. So these are called the chain terminating steps. So you need an initiation step to generate a few radicals, heat or light on a halogen. Then it just picks up steam, just feeds itself over and over and over again. Add these two elementary steps and you get the overall reaction. And then these are chain terminating steps where the process disappears. Now, doesn't matter which hydrocarbon I give you, this is methane, ethane, propane, butane, all the mechanisms are the same. See, so what you want to do is learn this mechanism. This is the only mechanism I'm going to ask you from this chapter. It's going to be give you any substance. So can you give me, if I give you this, pick on any hydrogen you want to. Let's take bromine and heat. You see delta means heat in organic chemistry. You see H nu means light. Give it a burst of heat, give it a burst of light, and let's say you get this product. Okay, so I'll ask you for the chain initiating step, the 2 chain propagating steps, and I probably won't ask you for all 3 terminating steps. I'll just say, give me an example of a terminating step. There's 3 to choose from. Okay. So, initiating step is the overall reaction. You can do something like this. You don't need to put the dots here, okay? Okay. And so you get bromine, right? You get 2 bromine. That's how you initiate the process. You just need a small amount of that, just a quick burst of Peter Wright in your business. Then, the first chain propagating step, and again, you don't have to put dots here. Just give me something like this. These dots here on this carbon. This will be the first chain propagating step. Should be a dot right there, nothing else. And then you got HBr. That's one of the 2 products. See, that was 1 product. Okay, now you're going to generate the other product. So this is the first chain propagating step. So, second step, this radical form. Step 1 will now collide with bromine. There's plenty of bromine. It's dumped in tons of bromine. So you form a bond, and that gives you the second product that we're looking for, brominated. And I get another bromine radical. So that can continue the process. Now step 1 can take place, and then step 2, step 1 is new. So these are called the chain propagating steps. Again, if you add these two elementary steps together, you cancel out this and this on opposite sides, this and this, you'll get the overall reaction. That's the way mechanisms have to work out, that you get the overall reaction. And then a chain terminating step, there's 3 possible chain terminating steps. I don't care which one you give me. You can have this radical and this radical collide. They annihilate each other basically. So once the radical is destroyed, the chain stops. Or you could have this radical and this radical collide. Where these are H's. And you get a product, but then the process stops because you're destroying the radicals. And finally, you can get 2 ethyl radicals colliding. And you would get butane. So you get a tiny amount of butane formed, just a tiny amount. It's one of the chain terminating steps. So anytime you bring together 2 radicals, that the process stops. And again, these radicals are present in tiny amounts, so most of the time they're not going to collide with each other. Most of the time, a bromine radical is going to collide with an ethane molecule because there's plenty of ethane. Most of the time, an ethane radical will collide with a bromine molecule because there's plenty of bromine molecules. But the radical concentration is always tiny. So that's the mechanism. It's very, very useful. It's the only way that carbon-hydrogen bonds really react. Otherwise, it does. free radical halogenation. Now, remember, the more stable an intermediate is, the lower its activation energy, the faster it forms. So, you need to be able to tell me where will free radical halogenation take place if you have a choice as to where it goes. Okay? So for instance, the stabilities, remember the stabilities? Methyl, these are hydrogens. A methyl radical is not that stable. A first degree radical is a little bit more stable. A second degree radical is even more stable. The most stable radical, the one that has the lowest activation energy, the one that's easiest to form, is the third degree radical. Okay? So if you got abstract hydrogens, see, this hydrogen is hard to abstract. This hydrogen is easy to abstract. When on the far left, if I abstract that hydrogen atom, I get a methyl radical. Very unstable, very high energy, hard to form. If I abstract this hydrogen, then it's easy to extract it compared to that one because I form a third degree radical. So the abstraction of a hydrogen can be predicted based on the stability of the radical that's formed. So given a choice, if a bromine atom was to react, it would react with this hydrogen here, most likely. So suppose you have something like this. And you add just a small amount of bromine, a small amount of light rather, or heat. And usually they don't add a whole lot of bromine or halogen. They want monohalogenation because they don't want a bunch of products. So you just usually add a small amount. If there's a possibility that it can go different places. Now, you can get bromination on these two carbons, give you one product. Bromination here gives you another product, here gives you another product, here gives you another. So you get 1, 2, 3, 4 different products. And if you have a large excess of bromine, you're going to get all of them. Okay? So you don't want a mixture. So if bromine can go different locations, they usually add a small amount so it only goes to one preferred spot. So can you predict the product? What will be the major product? Where will the halogen go? Which hydrogen will be abstracted? Well, look for a third degree hydrogen. If a hydrogen is attached to a third degree carbon, it's a third degree hydrogen. That's the one that's going to go. If you don't find any third degrees, you look for a second degree. Okay, so just go down the line. But there is one hydrogen that you can see. This hydrogen is attached to a carbon. It has 3 hydrogens and 3 carbons attached to it. This is a third degree hydrogen. That's going to come off the easiest. So if you do monohalogenation, just remember the reactivity. The third degree hydrogens come off the easiest. They form third degree radicals, which are more stable than the other types. Now again, if you had a large excess of bromine, you're going to get a mess. So they'll use a small amount of bromine in this case because they don't want a big mixture. But you're still going to get a mixture. So there's nothing you can do about it. The other thing to remember is hydrogens are attached next to a carbon-carbon double bond, or especially, these guys right here are especially susceptible to abstraction. Not these guys don't go. Not, well, this somewhat, but this is really, really subject to abstraction. And you're going to get 2 products, 2 major products. You had bromine. And let's get rid of one of these hydrogens. I don't make it carbon, just don't make it too messy for you. It's bad enough. Okay, so I'm going to ask you for 2 products if I add bromine in heat or light. I won't ask you for the mechanism, but you got to understand the mechanism. You got to understand that when this reacts, you got to abstract this hydrogen eventually. That's one of the propagating steps. And that's the hydrogen. These are vinylic hydrogens. Allylic, you can write it down. And allylic hydrogens are especially susceptible to abstraction because you get a radical like this that's stabilized by resonance, right? You can draw there's actually two locations. The radical is not concentrated just on this one carbon, it's spread out. Part's on this carbon, part's on this carbon. These are two resonance forms. See, so you get two products. So if you start with this and add bromine, eventually you're going to pull off this hydrogen and form this radical. The bromine can attack this radical or this radical. Now, what is it? It's a blend of these two pictures. Now, you might argue that this radical is a second-degree radical, so it's more stable than this because it's a first-degree radical, and that's absolutely right. But someone else could say, well, this is an internal double bond, this is a terminal double bond, so this is more stable. See, so this is more stable in terms of double bond location. This is more stable in terms of the radical location. So in fact, we get a mixture of both of these. Okay. Both of these resonance forms are important. They both make a contribution to the overall structure. So I would expect, I'll ask for two products. The two products would be the expected product, this, and the unexpected product, I guess you could call it unexpected, in which the double bond has migrated. And so you can get two products. So this is resonance now. This is two resonance. Okay, now, don't worry too much about this, but instead of using bromine, sometimes they use N-bromosuccinimide, and it's abbreviated NBS. Let me just show you what you might see. Let's get fancy with that. Just remember this. Carbons attached to a carbonous double bond, they don't leave. They're stay put. The guys next door are the ones that leave, okay? And so you can add bromine or chlorine and heat or light. But there's another way to do it. It's called adding NBS, N-bromosuccinimide, and it's the same thing. So when you see NBS, it stands for N-bromosuccinimide. Basically, you're adding bromine atoms. Okay. Both of these are ways to make bromine atoms. One is to shine light or heat elemental bromine. The other is to add this material called N-bromosuccinimide, and it just produces a small concentration of bromide ions. We won't worry too much about it. Just be on the lookout for that. So you can add bromine and heat or light to get substitution. Or this is N-bromosuccinimide, they shine light and get bromine. So, don't worry about that. Okay. So if you see either one of those, bromine and heat or light, NBS and heat or light, just usually light, that means they're generating, think this, bromine atoms. Okay? Okay. You'll get two products. Can you tell me the two products? I'm trying to get fancy, not doing this. Can you tell me the two products? First of all, remember you get a carbon here. These hydrogens don't go anywhere. These are called vinylic hydrogens. But you got hydrogens here, these are allylic hydrogens. So pluck off one of those hydrogens and form the radical. Then ask yourself, can I draw a resonance form? You'll say yes. I can move this electron here and move this one here, and then one here. Another radical would be here. See? So two resonance forms you're gonna get. What does a radical look like? It's a blend of these two pictures. So the bromine atom is sometimes gonna react with this picture, sometimes it's gonna react with this picture. So again, if you have analytic hydrogens, lots of times you're gonna get two products. This would be one. And then the other one, the double bond moves to a different location. Take a look at that, because that's can be confusing. All right, and like I said, there's not that many reactions, you know, so far we have free radical halogenation. I think there's only one other reaction, so two reactions get a master. Okay, let me show you something that's a source of much confusion.